Here we have an ellipse, x over 2 squared plus y over 5 squared equal to 1. If you set x equal to 0, you can get the y-intercept by solving for y, which will be 5 and negative 5. And if you set y as 0, you'll see that x equals to negative 2, and 2 are the two solutions. And therefore, connecting these 4 points, you get an ellipse. So this is the ellipse that you're given. And then inside here, you're trying to inscribe a rectangle. And among those rectangles, you're trying to find the largest one. So you're trying to inscribe a rectangle like this. Now, one way to do this is to call this point, the top right corner of the rectangle, as x comma y. Then because this length is same as this value x, the base length of this rectangle will be 2x, whereas the height of this rectangle will be 2 times y, because this length is y, so 2y. So the area is equals to 2x times 2y, which is equal to 4 times xy. Alright, because the question says we're trying to find the largest area. When you're looking for the largest of something, lowest, smallest, highest, all these questions have to do with optimization. Optimization questions usually have a structure where you have a target object for optimization. So we call this the target because we want to maximize this. And also some constraint between the variables. And in this case, we're given that x and y must satisfy this equation because x comma y is a point on this graph. So that's your constraint. Once you figure out what's the constraint and what's the target, then all you have to do is solve the constraint and plug it into the target, right? So let's do that. X squared over 4 plus y squared over 25 equal to 1 is from here. And then let's move it to the other side. Y squared over 25 equals to 1 minus x squared over 4. And then I guess you can just take the square root of both sides to get y over 5 equals to square root of 1 minus x squared over 4. And actually, when you're taking square roots, you should be writing plus or minus, but because we're only taking the top right corner, x and y are both positive, so we don't need the minus here. And finally, multiplying by 5, we have y equals to 5 times square root of 1 minus x squared over 4. Okay. Then once you solve for it, you can put that in to the target function. So the target function becomes a function of a single variable. So 4x times 5 times square root of 1 minus x squared over 4. And let's simplify this by moving the 4 inside. So actually you don't have to put 4 inside. We can put the 2 inside. So 2 times 5 is 10x. The remaining, so I'm splitting this into 2 times 2, and one of the 2 stays, and multiplied by 5 gives you 10. The other 2 goes into the square root and becomes 4, because 2 squared is 4, so when it goes inside the square root is 4, so it's 4 times 1 minus x squared over 4, which is 10x square root of 4 minus x squared. Okay, so that's your target function. When you plug in the constraint solved into the target, you end up with the target, which is just the function of a single variable. Then now all you have to do is some calculus. You differentiate. Now if you do the standard procedure for differentiating, you would need the product rule, and also when you differentiate this part, it will be chain rule. To save some time, I just calculated it. It's okay, so this is what you will get if you did all that procedure using the product rule and the chain rule. This is what you're going to get. Okay, so from this, the only way that this could be 0 is when x squared is equals to 2, right? If x squared is 2, 2 minus 2 is 0. That's the only way a prime could be 0, so we know that x is plus or minus square root of 2, but as we have assumed x and y are both positive, so we have x equal to square root of 2 as the only critical number. Now this area, when x is equal to 0 or y is equal to 0, when x is equal to 0 or y is equal to 0, the area is equal to 0, right? If x is 0 or y equal to 0, area is 0. So at the boundaries, the area becomes 0. What about when x is equal to square root of 2? Let's think about that. If x is square root of 2, you can plug this into here and get y equals to 5. Let me use a different color. That's y equal to square root of 5 times 1 minus 2 over 4. Square root of 2 is 2. So you end up with 5 times square root of 2 if you simplify. Okay, and then finally, when you multiply, you plug this into a, you get a equals to 4 times radical 2 times 5 times radical 2 over 2, which gives you 20. Okay, and since at the boundaries the value of a is 0 and at the critical number it's 20, this must be the maximum. So the maximum area is 20. So that's the answer. For the function f of x equals to 9x plus 4 over x, find domain and intercepts and all that, okay? So let's try this. Okay, first of all, domain. Domain is, you're allowed to plug in everything except when x is equal to 0. X equal to 0 makes the denominator equal to 0, so that's not good. So that means you are allowed to plug in everything except 0. So this is all reals except 0. Okay, for y-intercept, you have to plug in 0 into x in order to get the y-intercept, but that's outside the domain, so there's no y-intercept. And also, if you plug in y equal to 0 to get the x-intercept, 0 equals to 9x plus 4 over x. If you multiply by x, you get 0 equals to 9x squared plus 4. But 9x squared is non-negative, plus 4, that's positive, and positive can never equal to 0. So this doesn't work either. So x-intercept does not exist either. Okay. Now, to find where the graph is increasing and decreasing, you have to differentiate. Let's differentiate f prime of x. It's 9 minus 4 over x squared, which is 9x squared minus 4 over x squared. Right, you have to be careful. X equal to 0 is not a critical number because it's outside the domain. However, it is a possible place where there could be sign change. So when you draw the number line, you have to include x equal to 0 on the number line. Alright, what are the critical numbers? We need to set this equal to 0, but for a fraction to equal to 0, the numerator has to equal to 0. So this means 9x squared minus 4 has to be 0. X squared must be 4 over 9, so x must be plus or minus 2/3. Okay, so we have values 0, 2/3, negative 2/3, and then if I plug in negative 1/2 and 1/2 and 1 and negative 1, these are the test values. Let's see if I let's see if I plug in negative 1 here, it's 1 because it's squared. 9 minus 4 is positive. The denominator is always positive, so we only need to figure out what's the sign of the top, right? So negative 1 squared is 1, 1 times 9 is 9, 9 minus 4 is 5, that's positive. So f prime is positive here. Negative 1/2, negative 1/2 squared is 1/4. 9 divided by 4 minus 4, that's negative, because 9 divided by 4 is 2.25. So it's negative. And again, it's the same thing. If you take the 1/2 squared, that's 1/4 again. And plugging in 1 gives you 5 in the numerator, so it's again plus. Okay, so we know that the function must be increasing up till 2 decreasing and then decreasing again, and then increasing. Oh, actually, this is misleading because there's a vertical asymptote. We know that x equal to 0 is a vertical asymptote, right? So it's probably, to decrease, it's probably going like that, and to decrease, it's probably going like that. So that's the general shape of the function, okay? And from this, we know that at x equals to negative 2/3, there's a relative maximum, and this is a relative minimum. Okay, the next thing is, what about f double prime? F double prime is, let's see, positive 8 over x cubed. So x equal to 0 is outside the domain, but that is the point where there's concavity change. And if you plug in positive, that's positive. If you plug in negative to this, it's negative. So it's before 0, it's concave down. After 0, it's concave up. There is a change in concavity at 0, but because the 0 is outside the domain, there is no inflection point. So no inflection. Okay. Finally, let's figure out the coordinates of the relative max and relative min. So relative max is negative 2/3, comma f of negative 2/3. So what's that? Negative 2/3 plugged in here, that's negative 6. Negative 2/3, negative 6, so it's negative 12. Okay. Whereas for the relative min, it will be positive 2/3, and it will be exactly the same, but with the positive sign. So it's like this. Okay. So that's the relative minimum. Okay. All right. Now we from here, we know that concave up is 0 to infinity, and concave down is negative infinity to 0. From here, we know that increasing is from negative infinity to negative 1, and also 1 to infinity. Sorry, it's negative 2/3. I got confused. All right, 2/3 to infinity, and then decreasing is from negative 2/3 to 0, and also 0 to 2/3. Okay, if you put everything together to draw the graph, you will be getting the following. You will have at 2/3 and negative 2/3, you will have here you're going to get negative 12. This will be positive 12, so this is 12, negative 12. And because this is a relative minimum, it'll be like this, and we know that it's concave up. And here, this is a relative maximum, so locally it's going to look like that, and it's concave down. So that's the graph of this function. Okay, now we are going to do a lot of optimization and related rates question. Always, when you see something being maximized or minimized, that's optimization. If you see something like fast, how fast, what's the rate, these are related rate questions. And because they are approached differently, when you first have a word problem in front of you, you should first identify whether it's an optimization question or a related rates question. Okay, here, find the closest point on the graph of y equals x squared plus 4 to the point 0, 8. And this word closest probably means it's optimization. Let's see why. So the distance between a point on this graph, let's call that x, y, and 0, 8 is square root of the difference between the x coordinates plus the difference between the y coordinates. And if you minimize this distance, that's the closest point. The point that minimizes this distance is the closest point. So now it's definitely optimization because this is the target we want to minimize. And we're even given this equation which we can readily plug in. So we end up with square root of x squared plus x squared plus 4 minus 8 squared. Okay, and that's x squared plus x squared minus 4 squared, which can be simplified as x to the 4th minus 7x squared plus 60. Okay, if you expand this out using FOIL and simplify, this is what you're going to get. Okay. Now, normally you would just differentiate this, set it equal to 0 to find the critical points and all that. But here's a shortcut. Trying to differentiate square root of this is cumbersome because you need to use the chain rule. However, think about this. If you can minimize what's inside the square root, wouldn't that also minimize the square root included? So, see, we're only interested in the closest point, not the target value itself. So, because we're just looking for x and y values, or just x values, and then we're going to plug into this y equals x squared plus 4, we only have to minimize what's inside the square root. So, we're going to modify the target. So I'll just say the new function that we want to minimize is the thing inside the square root. So x to the 4th minus 7x squared plus 60. Okay, then this is very easy to differentiate. F prime of x is 4x cubed minus 14x, and then that's factored as 2x times 2x squared minus 7. And see, there is actually 2 points. If you drew the graph and saw what's going on, the graph of y equals x squared plus 4 is this, and here's 0, 8. So if you're looking for the closest point to this 0, 8, there's actually one point here, another point here. Okay. All right. So we can limit our search to just 0 and positive, and by symmetry we can just negate the negative positive x to negative x to get the other point. Okay, so we'll temporarily assume that x is bigger than 0. We're going to limit our search. Okay, and in this domain, the only place that this is equal to 0 is when this is equal to 0, and that's 2x squared equals to 7. So x squared is 7 over 2. Then you take the square root, so you have x equals to square root of 7 over 2. And at the same time, we have y equals to square root of 7 over 2 squared plus 4, because y is x squared plus 4. So you have 8 over 2, 7 over 2, 15 over 2 as your y. So we know that square root of 7 over 2 comma 15 over 2 is one point that minimizes. Well, we didn't really check that minimizes. We can check it by thinking about the boundary value. See, boundary is when x is equal to 0. When x is 0, what is this value? When x is 0, it's 16, right? What the other boundary is when x goes to infinity. That makes this go to infinity, right? What about this one? Is it going to give us something smaller than 16? That's our question, right? So if I plug this in here, that just gives you 7 over 2. And if I plug in 15 over 2 over here, that's 16 over 2, so it's actually 1/4. So it's like 3.75 square root. That's less than 2. So that's definitely less than 16. Okay, so just by checking, we know that this is the minimum, so this is the answer. Okay, water is filled in a cone-shaped bowl. Suppose the water is being sipped through a straw at a rate of 4 cubic centimeters per minute. If the cone is 3 centimeters tall with the radius 5 centimeters at the top, how quickly the water level is dropping. So here, the important thing is how quickly, because that really means rate of change. Okay, so let's try this. Drawing a picture always helps. So let's say you have a cone-shaped bowl. Who has a cone-shaped bowl? It's like so made-up question, but it's okay. Yeah. We only care about solving the question, right? So let's say you have some water filled in inside this. And then we have to figure out how quickly the water level is dropping, right? So we need to get a hold of this H. And this formula says that we need R also. R. And once we have R and H, we can talk about V. Okay? So now let's think about how to approach this. The water is being sipped through a straw at a rate of 4 cubic centimeters per minute. So something is decreasing. What is decreasing here? The water volume is decreasing. Okay. So that means dV dt is equals to negative 4 cubic centimeters per minute. Okay. And then if the cone is 7 centimeters tall with a radius of 5 centimeters at the top, so this is the dimension of the cone. This length is 5 and this length is 7, so that this is like 7. Okay. And then how quickly the water level dropping? So it's the rate of change of the water level. What's the water level? Well, see this H and R, maybe I should draw it like this. So with different color. Okay. So the red is the bowl. Okay. And this black here is the water. Okay. It's black water. Okay. And then R and H. So H is the water level. And since it's asking for how fast water level is changing, the question is how fast is dH dt when H is equal to 4? That's the question. Okay. And then we have V equals to 1/3 pi r squared H. So we have, yeah, that's all. So to review what we have so far, here's R, which is the radius of the top of the surface of the water. H is the water level. We're given the rate of change of V, and we're trying to find out the rate of change of H when H is equal to 4. And then we also have this extra information that the dimension of the bowl itself is 5 to 7. Okay, now if you look at this from the side, the water it's like this. Here's 5 and here's 7, but then there's the water here, and water level is H and R is this thing. Okay. Now, when you are solving related rate questions and you recognize a triangle, it's usually either of the two. Either you use the Pythagorean theorem or you use similar triangles. And of course, to use similar triangles, you need more than one triangle. And this is such a case. You have this 7 by 5 triangle, the big one, and the small triangle is H by R triangle, the smaller one. They're both right triangles, and of course, obviously, they are similar. So we should say what 5 is to 7 is what R is to H. Now, whenever you set up a rate, you can cross multiply. So let's cross multiply. 5H is 7R. And I can even solve this for R by dividing by 7. You get 5 over 7H as your R. And then I'm going to plug this into V. Okay. Now, why is that good? That's good because now I have V as a single function of H. Well, that's a little misleading. It's a related rates question, so every variable here, V, H, and R, vary with time. So they're functions of time. Okay. So 1/3 pi, 5 over 7, H squared times H. And if I simplify that, that's 25 pi on top And h squared times h is h cubed. And then bottom is 7 squared is 49. 49 times 3 is 147. Okay, so that's a relationship between volume and the height. And now what do? Once you have only those related variables you want, now you differentiate, right? So let's differentiate both sides. If I differentiate both sides, the left side you get dv dt. On the right side, h cubed differentiates to 3h squared, right? So it's 3 times 25 pi h squared over 147. But we're not differentiating both sides by h, we're differentiating by t. So h is a function of t, which should be brought out and differentiated by t. Okay. So this is the relationship that we get if we if we differentiate both sides, and we already know that dv dt, that's given as -4, so -4 is on the left side. 3 and 147 reduces to 49, and then h, we can plug in h equal to 4 now without any penalty because we already differentiated. This bar here means you can only plug in whatever is here after you differentiate it. Never plug this number before you differentiate. Okay, you're going to get an error if you do that. Okay, so but we already differentiated, so I can plug in h equals to 4. 4 squared is 16. 16 times 25 is 400. So you have 400 pi over 49 dh dt. This is when h is equal to 4. Okay, and finally, if you solve for dh dt, you have dh dt dividing to the other side, you get negative 49 pi, sorry, 49 over 100 pi. And the unit for that is h as a unit of centimeters, and then t has this unit of minutes, so that is the correct answer. Okay, 54. A 13-foot ladder is placed against the wall. So let's try to draw that picture. So here's a wall, and there's a ladder, 13, and it's dropping, so something's changing. So another thing that we should try to do is when you see something changing, probably a good idea is to assign variables for it. So as the ladder is falling down like that, sliding from the wall, this will go there, right? So this length from the wall is changing, and also the height of the ladder is changing. So we'll assign x and y for it, okay? Now the top of the ladder is dropping at a rate of 15 feet per minute. Okay, so that means how fast y is changing. dy dt is -15 because it's dropping, okay? And the question is how fast? How fast is x changing, dx dt, when the top of the ladder, y, is equal to 5? So that's the question. Alright, in order to make use of this, we need a relationship between x and y. So let's use the Pythagorean theorem. See here, there's only one triangle, which is one right triangle. This is the easiest type of related rates, the one where you just use the Pythagorean theorem and you're pretty much done. Okay. If you have more than one triangle, then that's when you have to think about using like triangles. Okay. So, but here it's simple. It's just this. Okay. Now let's differentiate both sides. X squared differentiates to 2x, but x is a function of t, which has to be brought outside to differentiate. So it's dx dt. Y squared, if you differentiate, is 2y dy dt. And on the right side, it looks complicated, but after all, this is just some number. Any constant differentiates to 0. So that's what we have. And then now, since we have differentiated, I can set y as 5 without any problem. So 2 times 5. We also have dy dt as -15. That's not a problem either. However, x is a problem because, as you can see, this is okay. Dx dt is what we're trying to find, so that's okay. But everything else we know except this x. So how should we find out what x is? Well, if you think about it, when y is 5, x has a specific value, right? What is that value? You can go back to this and plug in y as 5 and solve this. 13 squared is 169, 5 squared is 25, 169 minus 25 is 144. Taking the square root, you will find that x is equals to 12. Or some of you might just recognize the Pythagorean triple, 5, 12, 13. So x is equals to 12 here. Then we are ready to solve. So dx dt is bring this to the other sides. Okay, 2 times 5 times 15 divided by 2 times 12. These two cancel. They both have 3, so you can reduce. So the bottom you have 4, and on the top you have 25. Okay, so the answer is 25 over 4 feet per minute. Okay. Now in real life, often people like to use proper fractions over improper. So mixed fractions rather than improper. So let's use mixed fractions. This is 6 and a quarter, right? 6 and a quarter feet every minute. Okay. But usually in calculus, we like to use mixed, the improper one rather than the mixed one. Okay, here's another question. A person 2 meters tall walks away from a building at a speed of 1.8 meters per second. And on the window, there's a sniper and trying to shoot at this person. Okay, so maybe it's like a scene from a movie or something. Okay, who knows? Okay. All right, so here's what's happening. So here's the building, and there's this guy here trying to shoot, and this person is here. Let's just say this is the person. Okay, just make it simple. And the distance from the person to the building is 16. But this is changing. He's walking. So if something's changing, you want to assign a variable rather than the number. Okay. A common mistake is to put a number just because it's given a number. But just read the question again. He is actually walking away from the building at 1.8 meters per second. So this length changes, and we can actually write down 1.8 as the derivative of this x. So it's very important to put an x rather than 16 here. Okay, and then if we kind of make a simplified drawing to this, let's see. This is like a trapezoid. These two being parallel. This is 2. That's 26. Those do not vary, right? So here's what we have. We have, like, if you take 26 and subtract 2, this is 24. That doesn't change. Okay. And then this x does change, and this is the head of this person being aimed at. And the sniper's rifle is pointed towards him. So as he's walking away, the sniper's rifle is changing its angle. Okay, and we're trying to find the change of this angle here. Okay. Now let's go back with and try to use this picture somehow. Okay, a person 2 meters. That's already accounted for. This 2 and 26. We did 26 minus 2 to get 24 here. He's moving at a speed of 1.8. So if he's going away from the building, this is the building, then dx dt will be increasing, right? Dx dt is 1.8. That's the change of this length x. And then the question is, find the rate of change of this angle when he is 16 meters away. That's the question. And we're almost done. The only thing that we're missing here is what's the relationship between this theta and this x. We have to have some kind of relation because otherwise we don't have anything to differentiate with. Okay, if you go back and look at this picture, you see that x is at the opposite. We know 24, that's the adjacent. So you can immediately think about the tangent. What's tangent of theta? Theta is opposite over adjacent, so it's x over 24. Okay, so tangent theta being x over 24, now we can use this and solve, well, we can differentiate, okay? So we can say, we can just put this and differentiate. Let's see. Okay, I guess we can do this, all right? Okay, so let's differentiate both sides. If we differentiate, derivative of tangent is secant squared of theta. And remember, theta and x are both functions of t, so you have to pull it outside and attach d theta dt. Okay? On the other hand, x differentiates to 1, and if you pull the x and differentiate, it's dx over dt. And then, yeah, so it's pretty good. dx dt is 1.8. That's what we have to plug in. And remember, this is secant squared is 1 over cosine squared. So if I multiply to the other side, I get d theta dt as 1 over 24 times, this is 1.8, times cosine squared of theta. Okay. Now here's the problem. We need to know what theta is when x is 16, because when x is 16, definitely there's a value for theta, and we need that value in order to figure out what d theta dt is when x is equals to 16, right? So d theta dt when x is equals to 16, let's put that in here and see what happens. If this is 16, that's 24, we can use the Pythagorean theorem to find the length of that thing. So let me use my calculator. By the way, these optimization questions and related rates will be always appearing in the calculator section. Okay, so please bring the scientific calculator for this. All right, so if I do use my calculator, square root of 16 squared plus 24 squared, let's see, I get 28.84. Okay, so if I take the 16 squared plus 24 squared, then this is about 28.8. Okay, and because cosine is equal to, actually we need cosine squared. Okay, cosine is equal to, if I just say this is hypotenuse h, cosine theta is cosine theta is 24 over the hypotenuse h squared, and 1 over 24 times 1.8 times 24 times 24. 24 times this, 24 times 24, and that cancels this. H squared is 16 squared plus 24 squared, right? And if I compute everything, let's use my calculator again. 1.8 times 24 divided by 16 squared plus 24 squared. I get 0.052. So I get 0.052. Now what's the unit for theta? It's radians. What's the unit for time? This is in seconds. So it's 0.052 radians per second. That's the correct answer. Okay, a box with square base is shown left. What's the formula for the volume in terms of x and y? That's easy, right? Y times base times length times width times height. So this volume is x squared times y. What's the formula for the surface area of the terms in terms of x and y? Well, there are two ends with x squared, right? So these are squared. So surface area is x squared. You have two of them, right? And then what is this area? This is x times y, right? And how many do you have? 1, 2, 3, 4. You have 4 of them. Okay, so you can basically say that the formula is 2x squared plus 4xy. Okay, now part C is, what is the maximum possible volume if the surface area can be at most 40 square inches? So if you set S to be the maximum surface area possible, the question is, what is the maximum volume? Okay, so under this constraint, so this is your constraint, and that's your target. This is the one that you want to maximize. Okay, so this time it's a optimization question. Okay, okay. To solve these questions, you're always going to, well, almost always, you're going to solve the constraint for one of the variables and plug it in. Here, because of this x squared, it's hard to solve for x, so we're going to solve for y. So let's do that. This is 4xy. If you move the 2x squared to the other side, it's 40 minus 2x squared. Divide by 4x, it's 40 divided by 4x, and 2x squared divided by 4x, which is 10 over x minus x over 2. So that's your y. We're going to put this into v. So what is v? v is x squared times 10 over x minus x over 2, which gives you 10x, and minus 1/2 x cubed. Now we have to differentiate 10 minus 3 over 2 x squared. Set this equal to 0. So x squared is, let's see, 20 over 3, which gives you x as plus minus, but since x is the length, you should only take the positive. So x equals the square root of 20 over 3 is your x value that makes it maximum. And when x is this value, we can plug it back into this function here, or we can go back here. Okay, so I guess it's the same thing anyways. So let's just plug this back in here. So you get v equals to 10 times square root of 20 over 3 minus 1/2 square root of 20 over 3 cubed. Okay, and again, you can use your calculator to simplify this. So 10 t 20 divided by 3, okay, then minus sqrt 20 cubed divided by 3 cubed by 2. Okay. And you get 17.21. So that's the answer for this one. Okay. Approximately 17.21, and this is in cubic inches. So inches cubed. 17.21 cubic inches. At noon, ship A is 300 kilometers west of ship B. Ship A is sailing south at 35 kilometers. Oh, it's always better to draw the picture. So let's try to draw the picture, okay? So here's ship A. and ship A is 300 kilometers west of ship B. So I guess ship B is in the east, and this is 300 kilometers apart. Okay, and then ship A is sailing south at 35 kilometers per hour. This is sailing north at 45 kilometers per hour. Okay. And the question is, how fast is the distance changing? All right. Let's see. If you look at this, this distance is changing, so we should put a value there. So let's put an x there. This distance is also changing, so let's also put a value there. Then you end up with this triangle. I guess y is longer than x because it's faster, right? And we're trying to figure out how fast the distance between the ships are changing. So at some point, the ship A will be moved from here to there. Ship B will be moved from here to there. And we are concerned about the distance between the two. So let's put this as z. Okay. Now we can put this down here and move this x over here, and then we have a nice right triangle. So this time, although you see more than one right triangle, this is just Pythagorean theorem, because we have to somehow relate x, y with z, and they all lie in this single triangle. Okay. All right. First, what is dx dt? 35. What's dy dt? It's increasing at 45. Okay. What's the relationship between x, y, and z? Well, it's x plus y squared plus 300 squared equal to z squared. That's from the Pythagorean theorem here. Okay. So we have almost everything. We have the relation and rate of change of both variables, and then we just have to find out what dz dt is when t is 3. The reason I'm putting 3 is because it's 3 p.m. 3 p.m. is 3 hours after noon. So that's the question. Okay. So this is all the setup. Now let's try to solve it. How do we solve it? We'll have to differentiate. Okay. If I differentiate both sides, we can use the chain rule. So x plus y squared, square 2 comes down. It's 2x plus y, but x plus y, which is nested inside, has to be pulled out and differentiated. Note that both of them are functions of t, so if we differentiate x, we get dx dt, and if we differentiate y, we get dy dt. How about 300? That's just the constant, so when you differentiate, it just goes away. And how about z squared? That's 2z, and then z has to be pulled out and differentiated, so it's dz dt. Okay. dx dt is 35. dy dt is 45, so perfect. We can just do 35 plus 45, which is 80. So we have 2 times x plus y times 80 equals to 2z dz dt. 2 can cancel. Alright, since we successfully differentiated and simplified, now we can plug in what t equals to 3 means. Right, what does t equals to 3 mean? See, because we have to solve for dz dt, only dz dt should be here. The other ones should be determined. We have to figure out what x is, what y is, what z is when t is equal to 3. The easier one is when t is equals to 3, what x and y are. X is, so distance, which is the x, is time times speed. So we have time 3 hours, speed 35. 35 times 3 is 105. Okay, so that's your distance, 105. Okay, and 45 times 3 is 135 times 80. And then what about z? Well, z, we have to use this. since 105 plus 135 is 240, we have to figure out what z is when this is 240 and that's 300. And again, I will need the help of my calculator. So 240 squared plus 300 squared. Square root is what z is, and that's about 384.187. 384.2 dz dt. Okay, then finally when we solve for dz dt, this is 240 times 80 divided by 384.2, and that's 240 times 80 divided by 384.2 is about 50. This is about 50.0 kilometers per hour. Okay. All right. A boy released a balloon on a level field, and it is rising vertically at a constant speed, 1 feet per second. Okay. So let's say here's the boy. He's holding a balloon, and the balloon is released and it's going up. It's going up at 1 feet per second. Okay. Now the mother is watching the balloon 10 feet away from the boy. So the mother is 10 feet from the boy, and when the balloon is 15 feet above the mother's eye level, how fast is the angle of elevation changing with respect to the mother? So it looks like the mother is just looking at the balloon that's flying away and thinking, well, there goes the balloon, my boy's going to cry. So that's basically what she's doing, just staring at the balloon. Okay. Now if we draw a simplified diagram here, here's the mother's eye level, and the balloon's height, balloon is here. So this is the eye, that's the balloon, and the length from here to there is 10 feet, and this height is changing, so we need to put something, since it's the height, let's put y for it. And we're trying to figure out how fast this angle of elevation is changing, so we're trying to think about this change of this theta. Okay, and therefore we have this right triangle, and we need to use some trigonometry to solve this question. Okay, because it's involving angles. Whenever you have a rate of change question with angles, you'll have to expect that you're going to use trigonometry. Okay. Okay, so let's see. So y is going up at constant speed, so dy dt is 1. That's what this is saying. Okay, and then when the balloon is 15 feet above, so when y is 15, we want to know how fast the angle is changing. So that's the question. Okay? So this is given, and this is the question, and in order to answer this question, we better have a relationship between y and theta, and from this picture we see that tangent of theta is y over 10. Okay, so this is very similar to the other sniper problem that we just solved. We can just differentiate both sides, secant squared of theta, d theta dt, 1 over 10 dy dt. Multiply this to the other side, because this is 1 over cosine squared, that's going to reappear on the other side as cosine squared. Okay, and then since dy dt is 1, we basically have this. Now let's figure out what d theta dt is when y is 15. Well, when y is 15, we have the following picture. We have 10 here, 15 here, and then we don't know what this is. Let's just call this h, and here's theta. Okay. And therefore, this is 1 over 10. What's cosine? Cosine is adjacent over hypotenuse, so it's 10 over h squared, okay, because it's cosine squared. And what is this? 10 squared is 10 times 10. I like to do that because 10 cancels. In the bottom you have h squared. What's h squared? That's 10 squared plus 15 squared, right? 10 squared plus 15 squared is 325. 10 is up there, so it's 2 over, let's see, 65. Okay, so we know that d theta dt is 2 over 65 radians per second. You can also solve this by using a calculator. In that case, you would be getting 0.0307. So it'd be 0.03 radians per second. Okay. Okay, a cylindrical can without a top is made to contain 400 cubic centimeters of liquid. Find the dimension that will minimize the cost of the metal to make the can. Okay. So here you have a can, and top is not there, and the radius is r and height is h. Okay, and the volume of a cylinder is pi r squared, the bottom circle's area, times the height. And because we are trying to minimize the cost of the metal, what is metal used for? It's used to make the surface of the cylinder, right? So we have to actually figure out the surface area of this cylinder. Okay. Now, if you cut this cylinder, like here, if you cut it right like this and take this bottom off, the bottom is a circle of radius r, so that's not a problem. But then this side, if you cut it and cut it open, you end up with this rectangle whose length, or the base length, has to match with the circumference of this circle, because this has to wrap around this circle. So this side, it would be 2 pi r, whereas this height will be h. Okay. All right. So that gives us the area, the surface area of the metal that we're trying to use. So this part is base times height, which is 2 pi r h, and this one has the area pi r squared. Okay. So from these two, we know that the surface area, which is related to how much metal we need, is 2 pi r h plus pi r squared. Okay. Now, because we're trying to minimize this one, this must be the target. So this must provide us the constraint. What is the constraint? The constraint is that it has to be 400 cubic centimeters of fluid in it. So the volume has to be 400 equals to pi r squared h. And this one it seems to be easier to solve for h, so let's solve for h. H is 400 over pi r squared, and that can be plugged in here to get us 2 pi r times 400 over pi r squared plus pi r squared. Pi cancels. one of the r's cancel, and you end up with 800 over r plus pi r squared. Okay, now s prime. What's s prime? That's negative 800 over r squared and plus 2 pi r. Okay, set that equal to 0, and we solve it, and then that will give us the radius. Once we find radius, we plug it into h, and we're going to get everything. Okay, so after this is pretty much just calculator, so let's just do it. We can multiply r squared both sides to get negative 800 plus 2 pi. I want to use a different color just a minute. Okay, we can multiply r squared, so times r squared here, to get negative 800 plus 2 pi r cubed equal to 0. So that means r cubed is 800 divided by 2 pi, which means 8 and 2 reduces to 400. So it's 400 over pi, and r is the cube root of such a thing. Okay. Now I'm going to calculate that. Let's see, 400 divided by 3.141592, and then take the power of 0.30333, which is 1/3, and then if I do that, that's 5.038. So I can just say 5.03. So this is about 5.03, and then when I plug that into h, let's see what I get. 400 divided by times 5.0308 squared. Okay, and I get 5.03. Oh, it's the same thing. H also becomes 5. So from here, h also becomes 5.03. So answer is radius 5.03 centimeters, and the height is also 5.03 centimeters. Okay. A closed rectangular box with square base and a volume of 12 cubic feet is to be constructed using two different materials. The top is made of metal costing $3 per square foot, and the remainder of wood is costing $2 per square foot. Please find the dimension of the box for which the cost of the material is minimized. Okay. So we already did a square base one. Square base box. It's same thing, XX and Y. So the volume is x squared y, and that has to be 12 cubic feet. And since this is a requirement, this must be the constraint. Then we need the surface area. What's the surface area? Well, 2x squared, so that's 2x squared. And on the side there's x, y, and 4 of them. Okay, so that's the surface area. However, when you're taking the cost function, that's different. Cost function is, see, 2x squared is measured in square foot. Okay, so if I take that square foot for the bottom one, oh, no. Just the top. I thought that top and bottom was the same thing. Okay, sorry. So if we take just the top, which is x squared, that costs $3 per square foot. But the bottom one is $2 per square foot, and 4xy, these are still $2 per square foot. Okay. The reason that I'm doing this is because if you have $3 divided by the area, so money divided by area is what you get as $3 per square foot. That's what you got. Then to recover the money from this identity, you multiply area both sides. Then area cancels away, and you get money equals to 3 times the area. See, and the area is x squared, so that's why we do 3 times the x squared to get the money required to make the top. And similar reasoning can be applied here and there. Okay, so we have, after combining like terms, we have 5x squared plus 8xy. So we're trying to minimize this while maintaining this v. So let's solve the constraint now. So once we have these, that's the target. So actually this wasn't necessary. You didn't have to do that. Okay. So the target is now c equals to 5x squared plus 8 times x times. If you solve this for y, y is 12 over x squared, right? It's 12 over x squared. And you have to do that because you, so this is y equals to 12 over x squared. You want to reduce the target function as a function of a single variable. Okay, then 8 times 12, that's 96. So you have 5x squared plus 96 over x as your cost function. Okay, let's differentiate it. C prime is 10x minus 96 over x squared. So when you set this equal to 0, you end up with x cubed equals to 96 divided by 10. So x should be cube root of 9.6, okay, which is 9.6 is 2.13. Okay, so it's 2.13. Okay, feet. And when you get that value, y is 12 over x squared, so y is 12 over 2.13 squared. That's 12 divided by 2.66, okay, 2.66. So the answer is, it should be 2.13 by 2.13 by 2.66 feet. Okay, they're all in feet.